Okay, I'd like to demonstrate Le Chatelier's principle visually to you. And what you see on the screen are the two structures of an acid-base indicator, a real common one called phenolphthalein. It's got a strange sounding sound to it and a strange spelling. But I got this from our labs, and it's an acid-base indicator. Every general chemistry class pretty much uses this stuff. And the nice thing about it is it can tell you the pH of a solution. It can tell you if you're in a acidic or basic medium. So the structures of phenolphthalein are rather complicated. This structure on the left, we've talked about organic chemistry a little bit in this class, but those hexagon-shaped things are carbons. They're called benzene rings. But the point here is just to show you that the structure of the molecule changes depending on the pH of the solution. And I can illustrate this shift in equilibrium that occurs when you stress this equilibrium. So phenolphthalein is a weak acid. This is the acidic form, and this is the basic form. So when you have a bottle, inside this bottle here, there's sort of a competition. Some of the molecules look like this, some of them look like this. I would guess that the vast majority are in this form here because it's a weak acid. So that means that the equilibrium lies far to the left. But I can cause this equilibrium to shift by adding base. So what I've done here is just in these weighing dishes, I just have some distilled water. And over here I have some vinegar. I'm using average run-of-the-mill store-bought vinegar. It's about 5% acetic acid. It's a weak acid. So I'm just going to pipette in. I'm kind of guessing, but I'm just going to add in, I don't know, let's say 10 drops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I've made the distilled water slightly acidic. Now if I add the phenolphthalein to this mixture, it should stay colorless. I'll put 2 drops in. 1, 2. And you see there's no color change. That's because the structure in the vinegar solution, there's a lot of protons, there's a lot of hydrogen ions floating around. So the phenolphthalein molecule is in this form mostly, so it's colorless. It's clear, but colorless means it has no color. It doesn't mean it's clear. So now what if I have some KOH, potassium hydroxide. It's the same ingredient, similar ingredient that's in Drano. It's a very basic stuff. But when this dissolves in water, I have a lot of OH hydroxide ions floating around which react with protons. So I've made a solution here. So if I add some in, let's see what happens. So I've just thrown in some solid KOH into some distilled water, stirred it up, and made this basic solution. So if I pipette it in, you can see it turns pink. Well, let me stir that up a little bit. No, haven't added enough base. Let me add enough base that I can shift the equilibrium to the right. Think about why it's shifting to the right. Add more. Not quite there, I'm close. This is the same reaction you do if we do what's called an acid-base titration. You carefully add measured amounts of acid and base, and you can calculate the concentration of a solution. I'm almost there. I'm almost to the basic side. I'm almost shifting it this side. I'm trying to cause a shift. Think about why it's shifting to the right. I'm adding a source of OH ions. I'm almost there. I bet 2 more drops will do it. 1, 2. Maybe that was a little more than 2. There, now I'm to the pinkish side. It turned pink. Why did it turn pink? Because I added a lot of hydroxide ions. Those hydroxide ions will react with the two protons. When this colorless form, it's in equilibrium with its basic form, the pink form. And when that happens, it releases two protons to become this structure. This structure absorbs visible light and turns colored pink. This is pink because it's absorbing, this molecule is absorbing some of this white light from my lamp, and it's subtracting out some of the colors of the white light, so it becomes colored. You might have learned about that in grade school when you were talking about complementary colors. But now I've shifted the equilibrium to the right by adding OH ions. I've removed these. That's Le Chatelier's principle. If I remove a product by taking it out, the equilibrium shifts to the right. So remove a product, I shift it to the right. You can also cause a shift to the right by adding a reactant. But what's going on here is I'm removing a product, and I'm causing the equilibrium to shift in this direction to compensate for the removal of the protons. Now I can cause it to shift back to the left by adding some vinegar. So what if I just take some vinegar and pipette some in? Let's just try a couple drops and see if that's enough. Not quite. It's kind of a guessing game because I haven't carefully measured these solutions. Let me add 2 more. Stir. You can see now I've gone back to the colorless side. What happened there? This solution over here is acidic. It's a source of hydrogen ions. So by adding in hydrogen ions, I've caused the equilibrium to shift to the left. That's Le Chatelier's principle. If I cause a stress on an equilibrium, the equilibrium will shift away from that stress. So it's shifting away from the stress, going to this form, which is colorless. And I can go back and forth forever. I'll just do it one more time. Now I'm adding in OH ions, this stuff. So now that's going to remove these. Removing those protons is a stress. The equilibrium is going to shift in a direction to replace the protons. So it's going to shift to the right. 1, 2. Let's see. Stir it up. Went back to pink. Add some vinegar. 1, 2. Back to this side. So all I'm doing is causing a shift left and right depending on if I'm adding acid or base. Adding base causes a shift this way because it removes a product. Adding vinegar shifts it this way because I'm adding in a product. That's Le Chatelier's principle. Hope that gives you a better idea of what's going on.